Okay guys, what's up? Welcome back with our last class before spring break here. So we'll hopefully keep it relatively short. We don't have that much left to cover. We're just talking a little bit more about upper triangular matrices. So if you recall, last time we finished off with this super cool mind-blowing result. It said that if T was an operator on V, a finite dimensional vector space that has a basis such that T has an upper triangular matrix with respect to this basis, then the diagonal entries of that matrix, lambda 1 through lambda n, are such that T minus lambda 1i, product all the way down through T minus lambda ni, is the zero operator. So why this was cool, we noted last time, this means that P of T is 0 for the polynomial z minus lambda 1 all the way down product through z minus lambda n. This is a polynomial multiple of the minimal polynomial of T since it zeroes out T when you plug it in. Okay, super cool. So what this says, if this is a polynomial multiple of the minimal polynomial, it means that the minimal polynomial factors completely into linear terms, and these lambdas, at least some of them, must be the eigenvalues of T. Okay, now today, we're going to take it a little bit further, and we're going to start by proving this fact. So we're going to say, hey, let's suppose that T has an upper triangular matrix with respect to some basis of a vector space V that it is an operator on. All right, now the claim is that the eigenvalues of T are precisely the entries on the diagonal of that upper triangular matrix. All right, comparing to what we just said before, what this is saying is not just that these diagonal entries, this list of the diagonal entries on this upper triangular matrix contains the eigenvalues of T, but that these are all of the eigenvalues of T and precisely only those values. That is, it doesn't have any extra information, it's just the eigenvalues. That's super cool. Basically, it means that all of the things we worried about before with being able to factor the minimal polynomial down into linear terms, just, these degree 1 polynomials, all those things, all those concerns vanish entirely whenever you have upper triangularity with respect to some basis. This is a relatively powerful condition. Okay, let's prove it. Proof. All right, so start it off. How are we going to do it? Well, let's suppose first that V1 through Vn is a basis of V such that T, an operator on V, has an upper triangular matrix with respect to WRT, this basis. Okay. Let lambda 1 through lambda n be the diagonal entries of the matrix of T with respect to this basis. I.e., what I'm trying to say is that the matrix of T looks like this. It's got lambda 1 here, and we go all the way down through lambda n. Down here, everything is zeros, and everything up here could be whatever the heck else. Who knows? Let's put a star right there. So let me put a little note there. So what I'm trying to say is all zeros below whatever. Doesn't matter what's up above the diagonal. We're just saying it's upper triangular. Okay. So think about this. So T of V1 is just equal to lambda 1 V1, since after all the matrix of T is defined so that the first column gives the coefficients in a linear combination of V1 through Vn that you use to represent T of V1. Same thing with the next column. The second column has the coefficients to represent T of V2 as a linear combination of V1 through Vn, and so on. Okay. Hence, lambda 1 is an eigenvalue of T. And how do we know that it's an eigenvalue? Since v1 is not 0, as it is part of a basis of V. That is a linearly independent spanning set, and you can never have the zero vector in a spanning or in a linearly independent set. Okay, cool. Now, think about this. Then, for k between 2 and n, we have, okay, let's think about it. Let's write it out. So, t vk, well, this will be equal to the matrix of t. Now, this will be the 1kth entry, v1 plus dot dot dot, all the way down to the matrix of t. I will write it as the k minus 1th entry in the kth column, vk minus 1, because the last one, I know what it's going to be. It's lambda k, vk. And this is just because the matrix of T has its kth entry equal to lambda k, i.e. that's what I'm writing up here with the diagonals. Okay, so tvk minus lambda k vk, which we could just as easily write as t minus lambda k I vk, is in the span of v1 through vk minus 1. Oh, okay. Basically, all I did is I took this piece here and I brought it on over to get this chunk. See? And I could just rewrite that, and then all I had left was things from a linear combination of v1 through vk minus 1. That is something that's in the span. All right, nice. Therefore, here's what we can say. T maps the span of v1 through vk to the span of v1 through vk minus 1. Thus, oh, sorry, I shouldn't say t. I've made a small error right there, not t. What I want to say is I want to say t minus lambda k I. This guy right here. See? It sends vk into the span of v1 through vk minus 1. So if I take something in the span of v1 through vk, well, that part that was with the vk there, that gets mapped to something in the span of v1 through vk minus 1. And hence, we send this to that. Okay, cool, right on. One thing that's important to remember is that last time, like for the other k minus 1 basis vectors, we did show last time, and I'll zoom out really quick here to remind everybody of this. I'm gonna have to invert the colors right there from the note packet form. The span of v1 through vk, is invariant under T. Here, I'll zoom back in. The span of v1 through vk is invariant under T for each k, if v1 through vn is a basis of V and T is an operator on V. So it doesn't even matter if T has an upper triangular matrix. This is just always true. Okay, here. Oh, this is always true. Sorry, I'm speaking too quickly. This is always true whenever T has an upper triangular matrix. I'm getting all tongue-tied there. Sorry about that. So basically what I'm trying to say is the span of V1 through Vk is invariant under T for any k, that is any partial list of these basis vectors in order right there, is invariant under T precisely when the matrix of T is upper triangular with respect to that basis. So going back to our proof, we already know that the span of V1 through Vk minus 1 gets mapped to the span of V1 through Vk minus 1 by T. And indeed, the span of V1 through Vk gets mapped to the span of V1 through Vk. We're just making the slightly stronger statement that T minus lambda I sends the span of v1 through vk to the span of v1 through vk minus 1. We already know it sends it to the span of v1 through vk. What we're actually just saying is that that last vector in the list can be represented as a linear combination of v1 through vk minus 1 when you map it through t minus lambda ki. Okay, cool. So t minus lambda ki restricted to the span of v1 through vk, and by this I mean the operator on span v1 through vk. That is the slight abuse of notation where I'm also assuming that I'm modifying the codomain as well. Okay, so this operator right here, this satisfies the following by the fundamental theorem of linear maps. Dim span v1 through vk equals the dimension of the null space of t minus lambda ki restricted to span v1 through vk plus dim range, same thing. So I'll just draw that. I'll put like little quotes there just to save myself the time writing it. But this tells me, well, I know what the dimension of this is. This is k, and I know that these have the dimension of the null space here, t minus lambda ki, this whole thing, restricted to the span of v1 through vk. Okay, this thing, but I know what the dimension of the range is. Well, it is, at least I should say it is, this is greater than or equal to. Since the dimension of the range certainly, or maybe I should be more clear here. What I'm trying to say is that I know that the dimension of the range certainly cannot be k, right? The biggest it could possibly be is k minus 1, since it sends this to this. Everything you get out has to live in this k minus 1 dimensional subspace. So the dimension of the range is at most k minus 1. So if this is equal to that, and this thing can be no bigger than k minus 1, then k is greater than or equal to that. Another way to put this, if you want to think of it this way, have I gone backwards? Last day before spring break, right? This thing is equal to k here, right? Okay, that's this thing. I think I've written it backwards. Dimension of span k there, blah, blah, blah. Maybe I've gone the other way. Oh, yeah, okay, there we go. Yeah, it should be less than right here. Good. I'm just thinking through this on the fly. Sorry, I didn't write that part of the proof down. All right, so basically what I'm saying is the dimension of this could be smaller than k minus 1, but it definitely cannot be larger than k minus 1. So this is the absolute biggest it could be. This thing could just be smaller than that. Hence, same thing plus something potentially smaller, less than or equal to same thing plus the biggest it could possibly be. All right, cool. Well, if we just manipulate things, this says that 1 is less than or equal to the dimension of the null space of t minus lambda k, restricted to the span of v1 through vk. Sorry for the extra hassle right there with me getting the signs flipped for a second. Okay, but what this says, if you want me to zoom out slightly, but this says that t minus lambda k has a non-trivial null space. That is, lambda k is an eigenvalue of t. Do you see why this means that t minus lambda ki has a non-trivial null space? We've certainly proved that its restriction to the span of v1 through vk. Oh, I think I lost a parenthesis right there. Maybe I've lost a few parentheses. Okay, there we go. Its restriction has a non-trivial null space, but that means that the whole operator has a non-trivial null space since it agrees with its restriction on the span of v1 through vk. Okay, cool. So this guy is a non-trivial null space. That means it's not injective. That means there is some non-zero v such that t minus lambda ki v is equal to 0. That is, it has an eigenvector, right? Okay, so we've got lambda k an eigenvalue of t. Therefore, lambda 1 through lambda n are all eigenvalues of t. Now, for the reverse, now since the polynomial q of z equals z minus lambda 1 through product all the way down through z minus lambda n satisfies q of t is equal to the 0 operator by the previous result. That is, from last time, the last thing we proved, this thing, hey, take t, an operator on v, such that v has a basis with respect to which the matrix of t is upper triangular and has diagonal entries lambda 1 through lambda n. Then t minus lambda 1i, product all the way down through t minus lambda ni, is the 0 operator, right? Okay, this is just the observation we made about this polynomial here. Okay, going back over there, so I'm doing the exact same thing, I'm just using q to label it. Okay, by the previous result. So q is a polynomial multiple of the minimal polynomial, the min poly. Since the zeros of the minimal polynomial are the eigenvalues of t, this tells us that lambda 1 through lambda n contains all the eigenvalues of t. That is, we know all the zeros of q. It's lambda 1 all the way down through lambda n. We know that all of lambda 1 through lambda n are eigenvalues. The only thing that could really happen is that potentially there could be some missing eigenvalues. But if there was a missing eigenvalue, well, since q is a polynomial multiple of the minimal polynomial, that eigenvalue missing would be a 0 of the minimal polynomial and hence a 0 of q. Oh, so it can't be missing because these are the zeros of q. So this contains all the eigenvalues of t and only the eigenvalues of t. Very cool. All right, let's go a little bit further and basically summarize this whole thing with one really nice result that ties a bow on all of it. Okay, let's finish it off with a fun one. So here's the last little bit. All right, we're going to suppose that v is finite dimensional. T is an operator on v. Got t an operator on v, v finite dimensional. All right, here's the claim. T has an upper triangular matrix with respect to some basis of v, if and only if the minimal polynomial of t factors completely for some lambda 1 through lambda m and f. That is, it is z minus lambda 1 product all the way down through z minus lambda m for some lambda 1 through lambda m in the field. That is, all of its roots lie in the field, and so it factors completely. Okay, this is kind of cool because it says that upper triangularity is equivalent to the minimal polynomial factoring completely. Really neat, actually. It's kind of strange that just being able to write things, a square array of numbers in a particular form lets us know that a polynomial factors completely. That seems kind of crazy, actually, if you think about it for a minute. Normally, factoring polynomials is kind of hard. There's a lot of machinery going on under the hood that somehow lets us basically factor polynomials entirely, or if not actually getting our hands on the factorization, lets us know that it is indeed possible. Just from knowing that we can write that array of numbers, that particular array of numbers, in a nice, like, geometric-y configuration. It's actually pretty neat. So the proof for this one, in one direction is easy, and in the other direction, it's not exactly hard, but it's kind of a little bit lengthier. We have to do some induction. So this will be a great proof to end the week on. It'll be a fun one. See if you can follow along. It's a little bit lengthy. So first off, we'll do the forward direction. All right. So first, suppose that T has an upper triangular matrix with respect to some basis of V. Okay. Let's do alpha 1 through alpha n denote the entries on the diagonal of the matrix of T with respect to this basis. Okay. Now, define QZ to be Z minus alpha 1 all the way down product through Z minus alpha n. Then, Q of T is the zero operator by the previous results. Okay, cool. We've shown that all the way from last time, that if you have an upper triangular matrix with diagonal entries lambda 1 through lambda n, then if you take the polynomial z minus lambda 1 all the way down through z minus lambda n, that big product, you plug t in, you get back the zero operator. Okay, super cool. So Q of T is going to be 0 in this case. All right, sweet. Hence, Q is a polynomial multiple of the minimal polynomial of T. Okay. Therefore, the min polynomial is of the form. I'll write z minus lambda 1 through ... z minus lambda m for some, I'll write it this way, lambda 1 through lambda m contained in, too many squiggles on my set bracket there, alpha 1 through alpha n. Not enough squiggles on that one. There we go. That is, if it's a polynomial multiple of this thing right here, then that means that this thing is just the minimal polynomial times something else potentially. So the minimal polynomial is equal to some chunk of this big old product. Hence, you can take some lambda 1 through lambda m contained in the set A alpha 1 through alpha n, such that the minimal polynomial is z minus lambda 1 product all the way down through z minus lambda m. Okay. Wow, nice. Okay. That's what we wanted to show. Now, for the other direction. For the other direction, suppose the min poly of T in LV is of the form z minus lambda 1 all the way down through ... z minus lambda m for some lambda 1 through lambda m in the field. All right. Now, we're going to do induction. This is the idea. We do induction on m. Okay, here's the base case. Base case is easy. let's let m be equal to 1. Then the minimal polynomial is just z minus lambda 1. So t minus lambda 1 I is equal to the 0 operator, which says that t is just equal to lambda 1 times the identity, and hence it's just the identity. It just take your vector and scale it by lambda, and therefore, think about it real quick. MT is upper triangular with respect to any basis of V. Why? Well, all t does is it just sends a vector to lambda 1 times itself. Yeah? Cool. Okay, sounds good. It's going to be diagonal with respect to any basis, since it just sends those basis elements to lambda 1 times that basis element. All right, so its matrix will literally just look like lambda 1 all across the diagonal, and that's it, no matter what you choose for your basis. Okay, cool. So maybe I can write that. Since the matrix of T is then just lambda 1, lambda 1. And then who cares? Or in fact, I won't even say who cares. We know what it is. It's got zeros everywhere else. Okay. So, in the case that T is just a scalar multiple of the identity, its matrix just looks like this with respect to any basis. All right, sweet. Inductive step. Okay. Suppose our result is true for all. Now, what we'll say is that for all, say, like m less than some specific, for all, I'll say values less than m, which we'll specifically say is greater than 1. Since we did the 1 case, we need to assume that we're at least larger than that one. Okay. So we'll suppose our result is true for all values less than m, which is bigger than 1. Okay, that is, we'll suppose that having the minimal polynomial look like this tells us that we have an upper triangular matrix with respect to some basis. Suppose that the minimal polynomial of T is z minus lambda 1, all the way down through z minus lambda m for some lambda 1 through lambda m in the field. Then, that's what we've supposed to start with. Okay, so we're doing induction on m. We did the base case. We're doing the inductive step. I'm saying for the inductive step, we're supposing that our result is true for all values smaller than m. Now, yet again, I am just restating our supposition here that the minimal polynomial is of this form. This is not a new thing. I'm just restating our supposition in the inductive step so it's clear what I'm using. Okay, now, here's the idea. Then, let's let u be equal to, and I'll even make this like that's a big U. So I'll use little u's as well, but that's a big U. Let's let this be equal to the range of t minus lambda m I. That's an m. Okay. Now, notice u is invariant under t, since t minus lambda m I is equal to, and I'll write it this way, I'll write it as p of t for p of z, the polynomial z minus lambda m. Okay, so we know that the range of a polynomial of t is invariant under t. We proved that at the, I think in 5b, pretty early on, maybe even 5a. So pretty early on in this section, we proved that if you take a polynomial of an operator, you get something that is invariant under that operator. Nothing crazy. Or something, you get the range of that thing is invariant under the operator. Nothing too crazy. Okay. Now, the only reason we care about this is that we can say that hence t minus lambda m I, or maybe even I'll do this way. Let me write it like this. Hence t restricted to u. Once again, I'm using notation to mean by this the operator there is this is an operator. Okay, and we can see the following, that if little u is in big U, then t minus lambda mi v is equal to u for some v in v. Why is this? U is the range of t minus lambda mi. So everything in U is t minus lambda mi v for some v in v. Okay, cool. So we have an operator, right? And we have this. All right, let's see the following. Okay. So t minus lambda 1 I all the way down through t minus lambda m minus 1 I times this u, this little u, is equal to, well, the exact same thing, t minus lambda 1 I, all the way down through in the product, t minus lambda m minus 1 I, and then we're going to use this fact right here to get lambda m, t minus lambda m I v. But wait a second. This is the minimal polynomial of t evaluated at t. So this is 0v and hence is 0. Oh, okay. And we may conclude that z minus lambda 1 all the way through z minus lambda m minus 1, this guy is a polynomial multiple of the minimal polynomial of t restricted to u. Oh, okay, right on. So this is a polynomial that if you plug in t, zeroes out all the u's and u's, or all the u's and u, right? Take any old u and u, punch it in, bam, you get out 0. Okay, so it's a polynomial that zeroes out t restricted to u for sure, right? Because if you just only consider u's and plug in t, that's the exact same thing as plugging in t restricted to u and then doing it on its domain, right? Okay, cool. So this is a polynomial multiple of the minimal polynomial of tu. Whoa, okay. So the min poly of t restricted to u is of the form, now, I might run out of room here, we'll see. This is of the form z minus, I will write it this way, it is of the form, maybe I should be more clear, is of the form z minus, I'll write it as beta 1 all the way through z minus beta, let's call it t, how about? For beta 1 through beta t, this subset of coefficients contained in the subset of coefficients lambda 1 through lambda m minus 1. Why are we going through all of this hassle? Well, we've shown a base step, and so when we do our inductive step, we're supposing the result is true for all values less than m which we were saying is bigger than 1, but all values less than m. Bam! M minus 1 is less than m. Nice. Okay. So there is, let me even just take this last result here really quick before I keep writing. I'm just going to okay, there we go. Now I'm just going to get rid of that for just a moment. Okay, cool. So there is a basis by our inductive hypothesis such that t restricted to u has an upper triangular matrix. Let u1 through uk be this basis for u, or any such basis for u. So a basis that does this for u. Okay, now here's the idea. Then, so what we're going to do is we're going to extend this basis to a basis for all of v, and we're going to show that we get upper triangularity for the matrix of t. The way we'll do that is we'll show, and I'm going to go back to a previous result, we will show the following. We'll show that t of vk is in the span of v1 through vk. That is, we will show that the image of a basis element is in the span of the basis elements up to that basis element. That is, the image of the kth basis element is in the span of the first k basis elements. Okay. Then, so what we can do is the following. So we can say, hey, look, since it's upper triangular, t of uk, well, which is just t restricted to u, of uk. I guess I should say, yeah, so this is the basis. So t of uk, which is the same as t restricted to u of uk. So this is in the span of u1 through uk, right? Maybe I should even use a different thing than k. Here, yeah, how about this? I'll leave that as k, but just to make things super clear, since I have too many different things running around, I'm going to call this u big M. How about? There we go. For k between 1 and big M. Yeah? Okay. Now, extend u1 through um to a basis of v as u1 through um, and then I'll take a v1 through a vn. How about? Okay, cool. For k between 1 and n, we have, now I'm going to write this out in the following way. T of vk is equal to, and this is almost silly to write, t minus lambda m I vk minus, or sorry, plus lambda m vk. That is, I'm just adding and subtracting lambda m vk here, right? Nothing too crazy. So here, if you even want to see that, let me spell it out a tiny bit more. Okay, here. tvk minus lambda m vk plus lambda m vk. So I'm just adding and subtracting that, which is just giving me t minus lambda m I vk minus, or plus lambda m vk. Agree with this? Yeah, right? Because t of vk is equal to t of vk. Okay, nothing too crazy. By definition, that is by the definition of u, which if you'll recall is the range of t minus lambda m I, we get the following. So this says t minus lambda mi vk is in u. Okay. And this piece right here, t of vk, well, this is t minus lambda mi vk plus lambda m vk. I know what this is. Wait a second. So this says that t of vk is in the span of u1 through um v1 through vk. Since this piece here is in u, and then this piece here is going to go on right there for the vk. See what I mean? Oh, okay. Wait a second. I've just shown that t of vk is in the span of the first k elements, or of the basis up to vk. That is, tvk in the span of basis up to the same index as the thing I'm plugging into t. So we are done. Oh, why? Well, because this right here, this condition, is equivalent to the matrix of T having an upper triangular, or being upper triangular with respect to that basis. Oh, nice. So all we had to do was show that T of VK is in there. Ah, pretty sweet. Okay. All right. That's a pretty long proof. That's kind of a brutal proof to end the week with, but wow, a lot of fun. We really shoved it in at the end of it there. Hopefully that makes some sense. I hope I didn't get anyone confused with this big M right here. We only use that just for a second to denote the number of elements in the spaces for U. I just wanted to make it clear that this was a different number. Who knows what the dimension of the space is? It's just something that's less than the dimension of V. It doesn't really matter. The only time we use this is say, okay, it's for K between 1 and M right here, just for this piece. So nothing crazy. This is a big M right there. And over here, all of these are little m's, lambda of little m right there, since that's how U is defined, was in terms of that m. Okay, cool. So we finished that one. There's one tiny, nice little thing that we get out of this fact. That is, knowing that T has an upper triangular matrix tells us its minimal polynomial factors entirely. And knowing that the minimal polynomial factors entirely tells us that T has an upper triangular matrix. So here's a cool fact. I'll put it at the bottom right here over it. Suppose V is a finite dimensional complex vector space and that T is an operator on V. Then T is an upper triangular matrix with respect to some basis of V. Terrible line. Why? Well, every polynomial factors over the complexes. Oh, that's sweet. That's a nice little corollary. That's just a good little free result you get out of there. And with that, I think we're done for the week. Have a very good spring break. I'll see you after your vacation.